through various observing groups that, not in exact order of discovery, but basically, so Peter is representing the Fermi GBM team, providing the first ever electromagnetic counterpart to gravitational wave shifts.
Yes, so thanks, Brian, for having me here and all the organizers. So I'm going to talk about what GBM saw for this exciting binary neutron star merger. So I'm going to talk about these two papers we put out. One of them is led by Adam Goldstein. That describes only the GBM observations, agnostic of the mostly agnostic of the LIGO discovery. And there's the LIGO GBM, LIGO Virgo GBM, and the ACS collaboration that goes into the joint science. So I'm going to touch upon a few bits of joint science, but I obviously cannot cover all of that. So just a short rundown of my understanding of GRBs for those of you who are not in the GRB business. So we maybe focused on the GBM side. So we see a few GRBs a week. We have a catalog. This is how the sky looks in terms of GRBs. We think there are two kinds of GRBs. There are short duration, this is duration histogram, short duration GRBs, long duration GRBs. Spectra is really a mess. I mean, the main part is this here. This is a peak at a few tens, a few hundreds of keVs. We may have, for bright burst, different components, black body components, extra power law. It's not really relevant here. We have a variety of flight curves varying down to tens of milliseconds, and then we have afterglows that last weeks, maybe years in the brighter cases. So, but basically, this is the big picture. We have prompt emission going from keV to MeV energies, and we have afterglow going from radio to TeV, just short of TeV. So we have this picture that they have the isotropic equivalent energy of 10 to 51, maybe 55, and there's the jet.
55 is not for short burst, right?
Just GRBs. Yes.
Yeah. All so the short ones will peak out at 52 or 50.
Yeah, so they're on the lower side.
Yeah.
We should have put luminosity. Yeah, so this is a sketch of GBM. We have two types of detectors. We have a group of 12 NEIs pointing at different parts of the sky at lower energies and at higher, relatively high energies. We have BGO detectors, only two of them, and this is their arrangement here. We are turned on 87% of the time. Sometimes we cross the South Atlantic anomaly, then we have to turn off because there's huge particle activity and would damage the detectors. And at any given time, we see the entire unocculted sky, which is about 67%. So if you take a given location on the sky, you see it 60% of the time, roughly. So these detectors count the photons basically, and whenever the onboard software determines an increase, it sends out a trigger. And for our purposes here, for short GRBs, we see short GRBs triggered about 40 a year. And to increase our sensitivity, we do two other kinds of searches. So these were, the 40 per year are detected by the spacecraft, but we can do better, and we have two campaign search programs. One of them we call targeted, and that is of the G150914 GBM fame, the maybe counterpart of the first GRB event. This is very computationally intensive, and we only do it for interesting times. Interesting outside triggers. And we also have the untargeted search, where we just download the data and fit a better background search, more time scales than the onboard spacecraft, and we get about 80 extra short GRBs per year. So the way we localize these GRBs is we just compare two or more detectors intensity, and we know how they respond, and we can nail the GRBs in the sky. So, okay, this is the timeline of our discovery. Mm. So the gravitational wave came almost exactly 2 seconds before our instrument triggered. So the onboard spacecraft sent out a notice 14 seconds after it deemed that it had something interesting, and it sent out also a very rough localization map. So it looked something like the dashed line here. This is a sky map that Brad showed before, and these are the 3 detectors whose normals were pointing closest to the source. So first, everybody scrammed to their computers. It was early morning, and we knew that they were, about 30 minutes later, we knew that there were 2 seconds difference, and we only had one LIGO sky map, the 1 interferometer sky map, and that is all over the sky, so it's just an antenna pattern, but we were hopeful because it was pointing at this general direction, so we were consistent even with the single interferometer map. But then, as data kept pouring in, we had better localization, and the joint LIGO-Virgo map came in, and it fit nicely into our confidence regions. So if we distill the whole thing, this is how it looks. So this is our final best contour map. This is the LIGO-Virgo best map. So we compute the, yeah.
That's a 90% confidence
Yeah, I
area?
think so, yeah.
And so, since I have the floor, can you comment, is that typical for what you do?
Uh,
In that sort of sky location, that sky localization, or is
So
it sometimes better?
the weaker, the worse. It depends on the strength of the geometry. So we compute chance coincidence for this event. So the chance of getting GRB this close to a gravitational wave trigger, temporal coincidence, is 5 times 10 to the minus 6, and just from the rate of the short GRBs we see, and another factor of 2 comes from another 2 orders of magnitude come from the spatial coincidence. So we get it about 5.3 sigma. Okay, so this is how it looks. We just from the properties of the instrument, we check the 50 to 300 keV range because that's where GRBs are the brightest, and surely enough, this is brightest in the 50 to 300 keV. We triggered on a quarter-second time scale. We tried to do the duration. It came out to be 2 seconds. And so you look at this picture and you say, why is that 2 seconds? Because the peak lasts only about half a second. So we worked on this a lot. But when you look at, as Chet showed or Brad, when you look at it at lower energies, so there is something making our T90 the duration longer than the obvious half a second. So we went in and tried to get rid of this because we thought maybe just noise, but it was stubborn, and we do the T90 in the 50 to 300 kV range, and this guy here just peaked above 50 kV, so it was enough to skew our duration. But nonetheless, so this is the final answer. So yeah, this is the basic picture. We have a main peak, half a second, and a soft peak lasting about 1 second. So you may ask, is this related to the burst or coming somewhere else? We check, and it's consistent with the location. So we are sure it's coming from the burst. So then the next natural question is this really a short GRB or is it a long GRB? So if you just casually read the GRB literature, the common wisdom is that short GRBs are less than 2 seconds, long GRBs are longer than 2 seconds. So what we did is, so it's not that simple for GBM at least. We modeled the distribution of T90s, the durations, as 2 log normals, and put the GRB 1708, 17A on this distribution, and we found that it's 3 times more likely to be so it's around 75% likely to be a short and about 25 being the long.
Does that give you a handle on the panel? So neutron star versus neutron star black hole. Can you say something about ruling out the partner?
I don't think so.
No.
It's all has to do with the stuff that's going on very far away from you.
If that soft emission wasn't there, I think it would be much.
Yeah. So yes, that's why I said here it's really conservative. 2 seconds is really conservative. If it weren't there, we would be about here, and it's about more than close to 100%. Yeah, so we did 2 things in the spectral analysis phase. So we did a standard analysis when we select intervals to analyze like we do in other bursts to see how it compares to other bursts. And then we did a detailed analysis to get a count of all the flux we have. So this is how it looks. We have this non-thermal peak here in green from the 0.5 second long peak main pulse, and it's about 200 keV. And the soft component is consistent with a black body of 10 keV temperature. It has the energy in these two are for one of the other. Okay, so the soft component is about 33% of the hard component. Okay, it's turned out really small. You can't read it, but we compare many properties of this GRB with other GRBs that we see. So black histograms are the distribution of short GRBs. For example, this is the fluence. You can see, as Brad noted, that this is perfectly ordinary short GRB. It's dimmer than we see, and it's a bit softer, but yeah, nothing out of the ordinary, except for the short soft episode. Yeah, somebody says it's kind of a meh burst. Would have been just an afterthought when we do our weekly conference to decide to classify things. Okay, so some pieces of interpretation. This is the again the plot that Brad showed. This is really amazing. I need to show this anyway. So this is the neutron star merger, and it's about 1.7 seconds later. This is the integral. You can see about a 0.1 second 1 second long peak there, and our hard energy range and our softer energy range there. Yeah, we worked quite a lot on determining when it actually starts, because the trigger times are about 2 seconds, differ by 2 seconds, and we worked really hard to nail down that 1.7 second. Okay, so as you all know, so this is an ordinary GRB, but if you consider distance, it turns out to be dim by orders of magnitude. So it's really natural to do consider an off-axis scenario. When we did our papers, we weren't aware of every observational data, and we also considered what if this is an intrinsically dim GRB, that it's on axis. And there's other interesting things like speed of gravity that can be done there. So this is a very involved plot that deals with the GRB being off axis, and it's a top, we consider a top head jet. And these are the 3 scenarios we can come up with. But the thing is that, except for this one, and even with, in this case, the top head jet, there are so many free parameters and really not too much handle to constrain the free parameters. So what we do is take the gravitational wave. If we take the gravitational wave that only the viewing angle theta v is constrained only by only to 56 degrees, as we include distance measurements to NGC 4993, we get down to 36, and if we take the lower Hubble constant, it gets to be even lower. So this shows you how the duration of the off-axis relates to the on-axis case, and this is EP, and so it's just a ratio of Doppler factors, and it comes out to be this factor. We simplify it into this factor B, which is about is a function of Lorentz factor squared and the difference between the jet opening angle and how we view it. So it's what we do is this is what we observe, and we try to make it a normal GRB, so in the sense that an average GRB that we observe. So this is the EI, so very low, and we try to scale it with this B factor and end up with this kind of scaling. So we can make it 6 MeV EP, a relatively normal EISO, and a really short duration. And to get there, we need to maybe assume a 30-degree opening angle, Lorentz factor normal Lorentz factor about 300. But the problem here will be that the difference between the viewing angle and the jet opening angle has to be about 1 degree, which is on probabilistically unprobable, because you can imagine there's just a sliver of the 1 degree sliver of the sky, and right. Okay, but if we do 30 degrees, it's not so common with the Lorentz factors being of order 30, less than 100. But here we can do it because we don't have high energy radiation. We can get normal EP, T90, and EISO with viewing angles that are around 10 degrees off the jet opening angle. Okay. So just some missile, and how less than the time?
Sorry, maybe 5 minutes or something.
Okay. So just a few things. How do we make it work in the on-axis scenario? So that's not my idea, but somebody calculated, and I think it doesn't really work. But as Andy said before, you need a lot of material ejected before. So the main idea would be to have the prompt emission. The main peak of the prompt emission, which is non-thermal, made by the external shock, but the external shock is made while the jet is still optically thick, and the photosphere comes a few seconds later, and that the photosphere makes the soft peak. So that's one idea. So we can do speed of gravity if we define the difference between speed of gravity and the c like that. We can take this we end up with about 15 to 16 orders of magnitude, minus 15 orders of magnitude difference that we can constrain. So we assume that they started at the same time and they arrived, and the EM arrived later by 2 seconds because it's the velocity is less, and then we assume that the EM has started 10 seconds later, and the gravitational waves caught up, and that's how we end up with these constraints. Okay, so these are some joint VNS short GRB rates for O3. They're not too good, but maybe we see a few more, and the design sensitivity for LIGO is closer to 2. So what you may ask, if it were dimmer, would we have discovered it? And we did calculate that. So if it were about 30% dimmer than it is, we still have triggered on it. If it were about 50% dimmer, we would have still put out the circular based on our untargeted search, so it would have been a bit later. And the targeted search, which seems to be the most sensitive, would have still triggered if it were about 60% dimmer.
Is the choice of 10 seconds motivated by any particular?
Yeah. So if you can have dense photospheres coming out at the 10 seconds later. Yeah. Okay, so these are my concluding slides. So the two most exciting things about this is that GBM can see counterparts of gravitational waves, and that we may have settled that at least some of them come from non-neutron stars. Okay. Thank you.
Okay. Question? Over here? Back there.
Maybe a question to you, or could the jet recess into our view? Could the 2 seconds be a recession place?
2 seconds between the gravitational wave and the...
Yeah, the gamma rays come later because the jet is recessing.
Yes.
It initially affects this and then it comes on.
That's a very long time scale for precession. But I guess, like, I mean, if the disk were misaligned,
Yeah.
Yeah, Nick Stone did some calculations in the black hole neutron star case, but in that case you expect that you could have a misaligned spin between the black hole and the orbit. In this case, the black hole will be spinning in the same plane because it carries the angular momentum of the binary. So unless the neutron stars had really fast spins, then maybe you could create a black hole with a spin that was somehow not precisely
so
aligned.
due to neutrino emission, the asymmetric.
Okay. Yeah,
So
maybe.
you need to pick it up another 2 seconds later. Right?
Good for Andy. Marion?
So this discussion of short versus long GRBs, was this analysis made using observer frame T90s or
Yes.
a rest frame? Because I mean, when people do this discussion, they use observer frame, which is silly. But here you have all the, you have the distance, and then you should also perhaps use just also Fermi GRBs that have distances to just really properly do it in the
I
rest
think
frame.
I'm not an expert. I mean, yeah, to some degree, but when you do transform the T90s to rest frame, there's a lot of problems you need to take care of, and I think so you need to transform the energy range into rest frame, and you don't know.
Basically everything, not
Yes.
just the duration.
Yes, and it's really, you get a lot of error sources when you do that. Except and here you only have what you observe, and the bimodal nature comes from what you observe. We're not sure if this bimodal nature exists in the rest.
How low gamma ray energy can you detect? Say 15 keV, can you detect much lower? Sorry?
How low gamma ray can you detect?
Our lower limit is about 8 keV.
Okay, let's thank Peter again. Now we're moving on to the discovery of the X-ray counterpart, Rafaela. Is going to inform us about